Hello and welcome today. We're going to explore a topic that many people, even oil and gas industry safety specialists, often get confused about. What's the difference between LEL and LFL, or between UEL and UFL? And what exactly does MIE mean? These are not just technical terms. They define the point where a simple gas leak can turn into a fire or even a massive explosion. In this video, we'll clear up the confusion and explain this concept in a simple way. Stay with me. This is going to be an exciting and eye-opening session. First, I want to clear some definitions. The first one is LEL and LFL. It means the lowest gas concentration that can make a fire or explosion. Below this, the gas is too lean, is too weak, so we don't have any fire or explosion in this area. UEL and UFL. It means the highest gas concentration that can make a fire or explosion. Above this, the gas is too rich. We have too much fuel and we don't have enough oxygen for fire or explosion. And another important term is MIE, minimum ignition energy. It means the minimum energy needed to make a fire or make an explosion. This energy can be provided by runaway reactions, hot works, ignition sources, surface temperature, and even static electricity, fire and explosion. If gas leaks outside, it usually spreads in the air. If it burns, it's just a fire. But if gas leaks inside a room or equipment, it can get trapped. If the gas level is between LEL and UEL, a small spark can cause an explosion. So the key difference between catching fire or explosion is trapping. Please attention, the key difference between catching fire or explosion is trapping. Trapped gas is a potential for explosion, and gas dispersion in the outside usually make a fire. So remember, LEL equals with LFL, UEL equals with UFL, and it means the same thing in different conditions, trapped or not. Let's look at two gases, methane and hydrogen. Methane, or CH4, that fire or explosive range is between 5 to 15% percentage concentration. And for catching fire or explosion, need at least 0.28 millijoule of energy to ignite. It means MIE for methane. But hydrogen, or H2, can burn between 4 to 75% concentration. And for catching fire or explosion, need only 0.019 millijoule of energy. Even a small static spark can light it up. Let's show on a graph. This part is heart of this session, so please pay attention. If we draw a two-dimensional chart where the horizontal axis shows the percentage of gas concentration in the air and the vertical axis shows the energy needed for ignition or explosion, we first draw the chart for hydrogen. We mark the values of LEL, UEL, and MIE on the graph, and the result shows the conditions required for an explosion. The amount of energy needed is very small, so even static electricity from clothes or hair can cause ignition or explosion. That is why the strictest safety rules must be applied in areas where hydrogen is present. In the same way, we draw the chart for methane and define its explosion range. If we draw the two charts in the same space, the white red area shows the explosive range of hydrogen, and the blue area shows the explosive range of methane. By comparing them, we can clearly see how dangerous hydrogen is. I want to stress again that both ignition and explosion can happen. In this graph, we assume that trapping exists, so we focus on explosion. As you can see, the explosive range of methane is much smaller than that of hydrogen. This doesn't mean methane is not dangerous. It means methane is very dangerous, but hydrogen is extremely dangerous. This shows why hydrogen is more dangerous than methane. It can burn over a wider range and needs almost no energy to start. Now the question is why this is important. Because for hydrocarbons like methane, we control leakage with engineering controls, administrative controls like ventilation, gas detectors, ignition sources control, and other. But in any units that we face with hydrogen, we need even stricter safety rules because it burns across a very wide range and it needs almost no spark to ignite. Question for you. Where do you think the strongest explosion power happens in the graph? Closer to the LEL or closer to the UEL or between them? Write your answer in the comment below. If this video was useful for you, please subscribe to the channel, like this video and share it with your colleague and your friends. If you have any question, write below and I'll try to answer your question too. Together, we can build a strong process safety learning hub on YouTube. Thanks for watching and remember, stay alert, stay safe.